the next question that we got on the menu today is about capacitance, and it's asking about the formula and units. It's kind of a open-ended question, but let's rewind for a second. Capacitance only exists when we have capacitors. Capacitors. Now, let's think about the word capacitors for a second. It kind of has the same type of word structure, or a subword that we can find in here is like capacity, storage. These are kind of like just clues of what a capacitor means just by looking at the word itself. Like, it's got capacity, capacitor. What does it store? Well, it stores charge. Stores charge. Now, what do capacitors look like? Well, suppose we have an electric circuit like this. Maybe we got like a voltage source. We can call that V, voltage source. And capacitors look like this. And they literally look like this because they are like two parallel plates that are not quite touching. So imagine that these two calculators are like the parallel plates. They're very close together, and when you have a voltage across them, there will be some charge that accumulates on the individual plates. Let's say blue calculator is the positive terminal and purple is the negative terminal. There would be like a bunch of positive charges that are accumulating here and negative charges accumulating here, and there's going to be like a potential difference between those capacitors. Okay, so maybe if we had like positive charges accumulating there, negative charges accumulating here, and across those plates we're going to have a voltage like this. So that could be like V capacitor. Okay, now how will we find the capacitance formula? Okay, so what the capacitance is like, this is a property of a capacitor. A capacitor. It's similar to how, like, a resistance and a resistor. Well, the resistance is just the property of that particular resistor. So, the units for capacitance, are farads. And that's named after Michael Faraday, who is a very clever scientist a long time ago. And he's also behind Faraday's law. So, if you have a law and a unit named after you, you're probably pretty good at science. And but you don't write farads, you just write big F. And it might be tempting to say that, hey, that F stands for fun, but it's farads. And most commonly, you'll have millifarads, microfarads, sometimes even nanofarads, but those are going to be the most common prefixes that you'll have, because like if you have like 5 farads, that's a massive capacitance. So it's typically going to be small values like this. Okay, now how would you find it? Well, when I search up capacitor equations, we can see that that's not the one I want to start with. The one I wanted to start with is, if we only know like the capacitor and we don't know what it's acting like in a circuit, we can figure out the capacitance. How this is calculated is epsilon times A over D. Okay, this I'll explain what some of these things mean. C, that's the capacitance. Epsilon naught is the permittivity of what's in between them. Of material between plates. This, like, in general, should be given to you by the question. Yeah, so for example, like, sometimes you might just have nothing between, or not nothing, you might just have air between your parallel plates, and that would have a certain epsilon naught value. You might also have maybe like a piece of dielectric, maybe like a piece of plastic, something like that, between the parallel plates, and that will have a different permittivity. It's basically saying like how easily is like how well the material between them is able to store an electric field. Okay, but this will generally be given to you by the question. A is the area of the plate. And D, this is the separation of the plates, or distance between plates. So if we draw it more in like a 3D sense, like we got some square plates, this could be plate 1, and like maybe all the way back here we'll have like a plate 2 going here. So the distance like that between them, that's D. Like that, this would be the area, or maybe better to like draw it like that. I'll erase that first drawing. Okay, the separation is D, the area, the cross-sectional area is A, and there's going to be like some type of thing between here, maybe something like, whoops, not purple, that's a kind of dark. Let's maybe put a lighter color like light sky blue. In between them there's going to be something, and that's going to have a property of epsilon naught, which is just permittivity. Okay. And another equation that we can use to look into the capacitor, or one of the like important capacitor values, is the amount of voltage across the capacitor is proportional to the amount of charge that accumulates on the capacitor. And they're related through this equation. Q equals CV. This is voltage across capacitor. This is the capacitance, and Q is equal to charge on capacitor. Okay, yeah, and this could be another equation that you could use to that involves capacitance, and as well this is going to give you more insight on the inner workings of the circuit with the capacitor inside. Now if we wanted to take the time derivative of this, so if we did like d over dt of q equals d over dt of cv, c is constant. We know that the time derivative of charge is going to be current. So that's going to be I equals C. We can move that outside because it's a constant, and it'll be the time derivative of the voltage. Oops, not dV. It's a d over dt of the voltage. And this is another way that you could get meaning from knowing the capacitance, or if you want to solve the capacitance, if you know how the voltage is changing and you know the current going through it, this can help you solve for the capacitance. Okay, so yeah, hopefully this helps address the question. The unit's farads, named after Faraday, and there are multiple different ways or multiple different equations that involve a capacitor's capacitance. So yeah, fun stuff like this. So the above solution is good. Is good. And question should be more specific in what how capacitance values are expected to be used. Okay, cool.